Okay, guys, this is a video to review the Kinetics IB questions homework. Um, so hopefully you're watching this after you've already given the questions a try. So this is question 10. Which conditions must be met for a reaction to take place? Reactants collide with sufficient energy. That's true. Reactants collide with correct orientation. That's true. Reactants must be in the same state. That's not true. You can have the same state refers to solid, liquid, gas. So you can have particles react. A gas can react with a solid can react with a liquid, two solids can react. So I think three is wrong. And if three is wrong, then it has to be A. These two are both conditions of collision theory. I know this one didn't copy over very well. It's a little bit faint. I hope that you can see it. A piece of zinc was added to aqueous nitric acid, and the volume of hydrogen gas produced was measured every minute. The results are plotted on the graph below. So we talked about that. Measuring the volume of gas over time is a way of getting an instantaneous rate of reaction. The graph itself doesn't show the rate of the reaction, but the slope of the graph does show the rate of reaction. So that's the steepness of the graph. Which graph would you expect the same mass of powdered zinc was added to nitric acid with the same concentration? So the only difference what you care about is the difference. They said a piece of zinc versus powdered zinc. The powdered zinc has increased surface area and therefore will lead to a faster reaction rate. So faster means steeper. So you should be looking for a curve that's steeper. Now, you also need to, sorry for the writing here, it's with the little trackpad. You also need to look at the amount that is produced. They try to trick you here. So in the original graph, it made it up to 40 centimeters cubed of hydrogen being produced. Now, all you did was make the zinc powdered as opposed to a single piece, but it's the same amount, and it's the same amount and concentration of acid. So the amount of gas produced should still be 40, and that's why these two don't match. They seem to produce different amounts of gas. So it should be either A or B. Now, B seems to basically be the same if you check kind of where it is at a given time. B seems to be the exact same curve as the original. Now, we know that with the surface area increasing, we should increase the rate, and therefore our graph should be steeper initially to represent a faster reaction rate, a faster change in the volume, but it should end at the same place. So the best answer is A. It's steeper, but it has the same ending point because the amounts are the same. Another question here about graphs. So a student added 0.2 grams of calcium carbonate powder to 100 cm cubed of 100 mole per dm cubed HCl, hydrochloric acid. And they said that that one is in excess. So that tells us right away that the calcium carbonate powder, right, is the limiting reactant. So kinetics, I think, is pretty straightforward, but it does tie back in with some certain concepts from stoichiometry. Okay, so they added this calcium carbonate to the hydrochloric acid and measured the volume of gas that was evolved. The graph of the results is shown below. So which graph would be obtained if 0.2 grams of calcium carbonate powder is added to 100 cm cubed of 0.5 mole per dm cubed HCl, still in excess? Okay, so again, you're looking for what's different about the first condition from the second condition. The only thing that changed is in the first condition, they said the concentration was 1 molar, and now it's 0.5 molar. So the concentration of the acid has decreased, and that means there will be less frequent collisions, so it will be slower. So we know that our graph down below should show a slower reaction rate, which means less steep. So it should be flatter. That's the first thing that we're going to look for. In any graph, we're looking for the slope because that represents the rate. So if it's slower, then we're going to look for less steep. The other part has to do with the stoichiometry. We have to consider how much gas is being produced. Now, in this case, in both of the examples, they said that the HCl was in excess, and the limiting reactant, therefore, is the calcium carbonate. The calcium carbonate amount hasn't changed. And so if the limiting reactant amount doesn't change, then the volume of gas produced also shouldn't change. It'll be produced slower, but the same amount of gas should still be produced. So if they had said 0.2 grams of calcium carbonate, and now we were using like 0.1 grams of calcium carbonate, then yeah, we would only make half as much gas because we would have halved the amount of our limiting reactant. But we have lowered the concentration, we've lowered the moles of something that is in excess in both situations, so it doesn't matter. All it's going to do is affect the rate. So I'm going to get rid of C and D because both of those produce half as much gas. The final volume is only 25, in the original is 50. So it has to be either A or B. A seems to be steeper than the original, and B seems to be less steep than the original. So the one that matches what we figured out about the rate is that B is the best answer. It rises more slowly, but eventually reaches the same total volume of gas. 13. Under which conditions will the reaction between 1 gram of calcium carbonate and excess hydrochloric acid be fastest? All right, so they seem to be switching around two different factors. It's about the size of the calcium carbonate and the concentration of the acid. Well, I know higher concentration is faster, and I know powder is faster than one single piece. So C is the only one that remains. Powdered with higher concentration will be fastest. Which statements describe the action of a catalyst? It does not alter the delta H for a reaction. That's true. When we do enthalpy diagrams, we have reactants and products. The delta H is this part, and the delta H is set in stone for a given reaction. So that part doesn't change with the catalyst. The catalyst affects this part, the hill, the hurdle that the reaction has to go over. That's the activation energy. If you use a catalyst, then you would lower that hill. So the new activation energy would be significantly smaller than the previous one, the uncatalyzed one, but the delta H stays the same. So one is true. It doesn't alter the delta H. It increases the EA, the activation energy. No, that's definitely not true. And on Roman numeral questions, as soon as I get one that's wrong, I just go ahead and cross that one out because usually the answer reveals itself. It alters the mechanism pathway of a reaction. That's true, but it's not really a core thing that we would have talked about in the SL class because reaction mechanisms aren't really part of the syllabus. That just means that it allows the reaction to happen in a different way. Like the particles end up colliding maybe in a different way than they would if there was no catalyst present. But that's not all that relevant for the SL course. So again, sometimes these Roman numeral questions, the best thing to do is try to get rid of one. And once you do, check the answers. And usually you can choose even if you don't know all the statements. 15, consider, this is, see if I can get that box, give myself a little room. Sorry about that. Here we go. Okay, consider the reaction between gaseous iodine and gaseous hydrogen. Why do some collisions between iodine and hydrogen not result in the formation of the product? The I2 and H2 molecules do not have sufficient energy. That seems right. So remember we said for a reaction to happen, you have to collide with the right orientation and with sufficient energy to overcome the activation energy. So it seems like some collisions wouldn't result in the formation of product if those molecules didn't have enough energy. Now, this is a little bit confusing at this point. We haven't done equilibrium yet. They're saying it's because the system is at equilibrium. That's not a deciding factor for whether or not a collision can be successful. The temperature is too high. That doesn't make a lot of sense. Then the particles would definitely more likely have enough energy. And if the activation energy is low, then it's also likely that they would have enough energy. So really A is the only answer that makes sense. 17. Maxwell-Boltzmann curve shows the distribution of kinetic energies. Anyways, we should know generically what the Maxwell-Boltzmann distribution looks like, which is the shape of the curve for a sample at a higher temperature. So a higher temperature the peak should move to the right. So the average is going to higher kinetic energy, but it should be a lower curve, so it's broader, but not as high. Now, it's a little hard to tell when you go down here, which is the best answer. I think this one is clearly higher, so that's not going to work. This one is higher or about the same. I think the only one that really looks lower, and that's kind of the key thing I'm looking for, is it lower and to the right? I think A is the best answer. The C one has gone to the right, and it seems to have gotten a bit broader, but it's also seems to be just as high as the original. So I think that one is wrong also for how tall that curve is. Which are the appropriate units for rate of reaction? Well, the technical definition of rate of reaction is concentration per time. So I'm looking for the one that is concentration, moles per dm cubed. And per time, second to the -1, implies that it's per second. This one is not per second. This one is just time. And this one is just concentration. Curve X on the graph below shows the volume of oxygen formed during the catalytic decomposition of 1 molar solution of hydrogen peroxide. Which change could produce curve Y? All right, well, let's think about Y for a second. Y is less steep, so it means whatever the change is, it's now slower than it was before. But in addition to being slower, I've now made more oxygen. I've made more gas. So the slower you've changed something that has made it slower, but you've also somehow increased the moles of the limiting reactant. And in this reaction, there is only one reactant, so I must have done something to increase how much hydrogen peroxide I was starting with. Otherwise, I can't make more gas. For example, if I just make it colder, that doesn't change the moles of hydrogen peroxide that are in there, so it shouldn't change the volume of oxygen that is eventually formed. And it certainly wouldn't make any sense for it to lead to more oxygen being formed. So I've got to think about something that increases the moles of the H2O2, the hydrogen peroxide, while at the same time matching up with our different factors that could slow a reaction down. So if I add water, that would definitely lower concentration, which would make it slower, but it would definitely not make there be any more moles of H2O2. So A is wrong. Adding some 0.1 mole per dm cubed hydrogen peroxide solution, that seems like a pretty good match, because what I already know is I have to add more hydrogen peroxide somehow, and I'm adding a more dilute version of the solution. So that means it would overall, the concentration would go down and it would be slower. I'm going to go ahead and say I think B is going to be the answer, but let's double check. Using a different catalysts do not affect how much product is made. They simply make it faster. So, or I guess if it's a different catalyst, it could make it slower, but it's not going to lead to more product. And lowering temperature is definitely not going to lead to more product. So it's all about actually the height of this one. They gave you some different factors that would make it slower, but you need to also realize that it's about the rate, but also the end point of the graph, and that you have to adjust the moles if you're going to change where the graph ends up. Which conditions would be the fastest? Well, they've given us some temperature values and they've given us volume and concentration values. So I'm going to go ahead and cross out the lower concentrations, and I'm going to go ahead and cross out the lower temperatures. And that leaves me with only one possible answer. Which experimental procedure could be used to determine the rate of reaction for the reaction between a solution of cobalt chloride and concentrated hydrochloric acid? Okay, so this is one where they want to know about the experimental methods involved. Could you suggest something that would work, that you could monitor over time to measure this reaction rate? I think what people like to go to are things like change in mass, change in volume, because those get used the most often with reactions that produce gas. But in this one, there is no gas. It's just things that are aqueous. So I don't think that there's going to be a change in mass over time or a change in volume of the solution over time, because it's just a bunch of stuff that's dissolved in water. It's all these aqueous ions. So I think B and D don't seem like good answers. So I'm down to measuring pH and measuring color with a colorimeter. If it tells me to measure pH, I'm looking for H plus ions and I'm looking for OH minus ions. I don't see either of those in this question, so I don't think measuring pH is really going to be useful here. It doesn't look like the pH is really going to change much, according to what I'm seeing. So then the last one, using a colorimeter to measure change in color. Now, okay, maybe you aren't aware of this, but I think it's kind of your only option that would make any sense. They don't really cover transition metals in the SL syllabus, but transition metals, their ions often have very strong colors. And you've seen that with copper 2+ ions, where they have that vivid blue color. So perhaps something about, there's a possibility of there being colorful ions in this situation. So this one is a little tricky. It sort of, it implies that you have a little bit more background knowledge perhaps about that topic. But I think, again, if you're a good test taker, if you don't sort of freak out when you see the question, you get rid of ones that don't make sense for this one, and you're left with the only answer that could make sense. Okay, if we move on to paper 2 questions, the graph below shows the volume of carbon dioxide gas produced against time when excess calcium carbonate is added to 2 molar HCl. Gave you the reaction here. Okay, so this is the curve. That's pretty standard at this point. State and explain the change in the rate of reaction with time. Outline how you would determine the rate of the reaction at a particular time. Okay, I'm going to switch over to this now. The different points that they're going to be asking you about. And let me change my font here because that's going to be way too big. That work? I feel like my font's still giant. Yeah. So what they care about, I think, is that the beginning of the curve, it's very steep. And as we go on in the reaction, it starts to get less steep, and eventually it gets flat. So it says, state and explain the change in the rate of the reaction with time. Well, the rate of reaction gets slower over time, or decreases over time. Fastest initially, and eventually goes to 0. So eventually there is no rate. That's when the curve gets flat. Now, how could we explain that? Well, initially, the concentrations, or the concentration of hydrochloric acid, which is HCl, and the amount of calcium carbonate, which is CaCO3, are at their highest. So the collision frequency is highest. And I'll make space for this answer in a second. But your answers are going to come back to mark scheme wording about why different factors affect reaction rate. And one of the key terms to remember is collision frequency, or how often particles are happening. So there's something about how at the beginning it's fastest because there's so many particles around that they are going to collide into each other very often. Not just that there's a lot of collisions, but that they are a lot of collisions per time. And I can summarize that in collision frequency. So they bump into each other the fastest at first. Over time, the collision frequency slows down, so the rate slows down. I think I'm writing way more than would actually be on the mark scheme. But over time, the reactants are used up. That specifically would be like the concentration of HCl and the surface area of the calcium carbonate both decrease over time, and that means collision frequency decreases over time. And eventually the limiting reactant is used up, and therefore the reaction stops. There's no more collisions possible that will yield the product. And then the second part is outline how would you determine the rate of reaction at a particular time. You would draw a tangent line to the curve at that time and determine the slope of that line using rise over run. So simply on the graph, figuring out 2 different coordinate points on that line, and you get the rise over run, you get the slope. So that hits all the points. That's probably more detail. If I was answering 4 marks, you could maybe skip the first statement, since it's sort of inherent in what you follow up by saying initially the concentration and amount or surface area of the calcium carbonate are highest. So the rate is the fastest because of the greatest frequency of collisions. Something about them getting used up, frequency of collisions going down. And I'd probably try to comment on the end, which is that the limiting reactant is used up, so the reaction stops. The 3 of the marks would refer to that type of, to describing the curve. The last part is pretty clear. You'd have to probably mention the drawing of a tangent line and that it's the slope of the tangent line that matters. In the next part, it says the On the graph above, draw and label curves if the same volume of 1 molar HCl is used. So same volume, but now originally we had 2 molar, now we're using 1 molar. And then in the next one, it says double the volume of 1 molar is used. Okay, so 1 molar is half the concentration. If concentration is probably the trickiest factor that could be changed in a graph question like this, because concentration is linked to moles. N equals CV. So in the first one, Roman numeral I, if I leave the same volume, but I use half the original concentration, so if I use half C times the original V, I'm going to get half the moles that I had in the original. In addition, because it's half the concentration, it's going to be slower. It's going to be about half as fast. Whereas in Roman numeral 2, if I use half the concentration, but I double the volume, those two changes cancel for the moles, and so I get this equal moles to the first curve. So that means that the endpoint should be the same. However, it should also be slower because it is half the concentration, and lower concentration is less frequent collisions. So if I had to draw these, I think the first curve would go like this. Sorry, it's so messy. The key is that it would be lower, about half as high, and that I draw it and label it. And it's slower at first. It's less steep. Ideally, it wouldn't do that funny thing, but again, I'm drawing on a trackpad, so forgive me. And then number 2 would start like this one, but it would keep going because there's more moles. Eventually, it would get to the same place as the original because the moles are the same. So that's two distinct points, right? The rate of reaction is how fast it is initially, how steep it is initially, and then how have the moles of limiting reactant been changed? In the first one, they've been halved. In the second one, they haven't been changed. So that determines how high up it ends on the x-axis. And so, yeah, I think I've kind of walked through the explanations already, so I'm not going to restate them now. 35. You've got hydrogen peroxide solution was placed in a boiling tube and a drop of liquid detergent was added to create a layer of bubbles on top of the solution as oxygen gas was released. The tube was placed in a water bath at 75 degrees C, and the height of the bubble layer was measured every 30 seconds. So that's how they're measuring the rate. They're measuring the height of the bubble layer over time. A graph was plotted of the height against time. Explain why the curve reaches a maximum. Well, it reaches a maximum because eventually all of the hydrogen peroxide has been used up. It has all decomposed. So when the reaction finishes, that means your limiting reactant is used up. In this case, there is only one reactant. So pointing out that that one has been totally consumed or decomposed, used up, that would be fine. Use the graph to calculate the rate of decomposition at 120 seconds. So here's 120 seconds. So at this point, they want to know what's the rate at this point. So this is what we were talking about before. You've got to draw a line on this curve. And I don't think I did a very good job, but I'm going to fix it. I'm going to get rid of that one. Take that one. Now, obviously, you don't have a tool like this, but you would have a ruler. So you would draw a tangent line. So you're drawing something that is as close to that curve as you possibly can get. So I've done that. And then I would pick 2 points on that curve. I could pick the one here, which appears to be 120 and 4. That's a good choice. I could go, down here and pick one, another point. Anyways, you pick 2 points on the curve on the grid. They're going to accept a range of answers for the rate, but you pick 2 points. So if I picked 120 and 4, and then I picked 0 and on my graph about 1.7, then I would do rise over run. So I would do 4 minus 1.7 is a 2.3 rise, and I would do 120 minus 0, so 2.3 divided by 120, and that would give me my rate value. I would report whatever that decimal was. And then I would want to report it with the right unit. The unit would be millimeters per second, because that's the units of the rise over the run. So anytime they ask you to get a rate at a particular time, you've got to add a tangent line, pick 2 points that are on that line, and do rise over run calculation. Okay, final 2 questions. 39. The rate of this reaction can be studied by measuring the volume of gas collected over time. Sketch a graph which shows how the volume of gas changes with time. Well, I think we've seen enough of those to know that if I have to do this, if that's time and that's volume of gas, gas is a product, so it starts at 0, it goes up quickly at first, starts to go up less quickly, and eventually it plateaus. That is the generic shape of these graphs when we monitor something over time. The gas is a product, so it increases and eventually stops increasing. 40, sketch and label a second Maxwell-Boltzmann energy distribution curve representing the same system at a higher temperature. Higher temperature still starts at the origin, still doesn't touch the axis on this end. It needs to have a peak that is further to the right, so a higher average energy, but therefore it needs to be lower. So something that's lower and further to the right, and something like that. Anything in that ballpark is going to get you the mark. Explain why an increase in temperature increases the rate of the reaction. Well, again, that's kind of the point of this Maxwell-Boltzmann distribution. I wouldn't do this on my actual test question. I'm just showing it to you. Because of the higher temperature, there are now many more particles that have energy greater than or equal to the activation energy. That's the first part, the first mark. And the second thing is that since the particles have more energy, more kinetic energy, they are moving faster and therefore they collide more often. They collide more frequently. So there's two reasons why temperature affects reaction rate, and you should always be prepared to state both. And so those are the answers to the questions, the homework questions. I hope that was helpful.